A geostationary orbit, geostationary Earth orbit or geosynchronous equatorial orbit, is an orbit whose position in the sky remains the same for a stationary observer on Earth. This effect is achieved with a circular orbit 35,786 kilometers above the Earth's equator and following the direction of the Earth's rotation. An object in such an orbit has an orbital period equal to the Earth's rotational period, and thus appears motionless at a fixed position in the sky to ground observers. Communications satellites and weather satellites are often placed in geostationary orbits, so that the satellite antennas which communicate with them do not have to move to track them, but can be pointed permanently at the position in the sky where they stay. Using this characteristic, ocean color satellites with visible sensors can also be operated in geostationary orbit in order to monitor sensitive changes of ocean environments. A geostationary orbit is a particular type of geosynchronous orbit, the distinction being that while an object in geosynchronous orbit returns to the same point in the sky at the same time each day, an object in geostationary orbit never leaves that position. The notion of a geosynchronous satellite for communication purposes was first published in 1928 by Hermann Potocnik. The first appearance of a geostationary orbit in popular literature was in the first Venus equilateral story by George O. Smith, but Smith did not go into details. British science fiction author Arthur C. Clarke disseminated the idea widely, with more details on how it would work, in a 1945 paper entitled Extraterrestrial Relays Can Rocket Stations Give Worldwide Radio Coverage? Published in Wireless World magazine. Clarke acknowledged the connection in his introduction to the complete Venus equilateral. The orbit, which Clarke first described as useful for broadcast and relay communications satellites, is sometimes called the Clarke Orbit. Similarly, the Clarke Belt is the part of space about 35,786 km above sea level, in the plane of the equator, where near geostationary orbits may be implemented. The Clarke Orbit is about 265,000 km long. Practical uses. Most commercial communications satellites, broadcast satellites and SBAS satellites operate in geostationary orbits. A geostationary transfer orbit is used to move a satellite from low Earth orbit into a geostationary orbit. The first satellite placed into a geostationary orbit was the SYNCOM-3, launched by a Delta D rocket in 1964. A worldwide network of operational geostationary meteorological satellites is used to provide visible and infrared images of Earth's surface and atmosphere. These satellite systems include, the United States GOES, Meteosat, launched by the European Space Agency and operated by the European Weather Satellite Organization, EUMETSAT, the Japanese MTSAT, India's INSAT series, Astatite, a hypothetical satellite that uses a solar sail to modify its orbit, could theoretically hold itself in a geostationary orbit with different altitude and/or inclination from the traditional equatorial geostationary orbit. Orbital stability. A geostationary orbit can only be achieved at an altitude very close to 35,786 km, and directly above the equator. This equates to an orbital velocity of 3.07 km per second or a period of 1,436 minutes, which equates to almost exactly one sidereal day or 23.9344612223 hours. This ensures that the satellite is locked to the Earth's rotational period and has a stationary footprint on the ground. All geostationary satellites have to be located on this ring. A combination of lunar gravity, solar gravity, and the flattening of the Earth at its poles causes a precession motion of the orbital plane of any geostationary object, with a period of about 53 years and an initial inclination gradient of about 0.85 degrees per year, achieving a maximum inclination of 15 degrees after 26.5 years. To correct for this orbital perturbation, regular orbital station-keeping maneuvers are necessary, amounting to a delta V of approximately 50 meter per second per year. A second effect to be taken into account is the longitude drift, caused by the asymmetry of the Earth. The equator is slightly elliptical. There are two stable and two unstable equilibrium points. Any geostationary object placed between the equilibrium points would be slowly accelerated towards the stable equilibrium position, causing a periodic longitude variation. The correction of this effect requires orbit control maneuvers with a maximum delta V of about 2 ams per year, depending on the desired longitude. Solar wind and radiation pressure also exert small forces on satellites which, over time, cause them to slowly drift away from their prescribed orbits. In the absence of servicing missions from the Earth or a renewable propulsion method, the consumption of thruster propellant for station-keeping places a limitation on the lifetime of the satellite. Communications. Satellites in geostationary orbits are far enough away from Earth that communication latency becomes significant, about a quarter of a second for a trip from one ground-based transmitter to the satellite and back to another ground-based transmitter. Close to half a second for a round-trip communication from one Earth station to another and then back to the first. For example, for ground stations at latitudes of IA equals AA plus or minus 45 a degree on the same meridian as the satellite, the time taken for a signal to pass from Earth to the satellite and back again can be computed using the cosine rule, given the geostationary orbital radius r, the Earth's radius a and the speed of light c, as. Note that r is the orbital radius, the distance from the center of the Earth, not the height above the equator. This delay presents problems for latency-sensitive applications such as voice communication. Geostationary satellites are directly overhead at the equator, and become lower in the sky the further north or south one travels. As the observer's latitude increases, communication becomes more difficult due to factors such as atmospheric refraction, Earth's thermal emission, line-of-sight obstructions, and signal reflections from the ground or nearby structures. At latitudes above about 81 a degree, geostationary satellites are below the horizon and cannot be seen at all. Orbit allocation. Satellites in geostationary orbit must all occupy a single ring above the equator. The requirement to space these satellites apart to avoid harmful radio frequency interference during operations means that there are a limited number of orbital slots available, thus only a limited number of satellites can be operated in geostationary orbit. This has led to conflict between different countries wishing access to the same orbital slots and radio frequencies. These disputes are addressed through the International Telecommunication Union's allocation mechanism. In the 1976 Bogotá Declaration, 8 countries located on the Earth's equator claimed sovereignty over the geostationary orbits above their territory, but the claims gained no international recognition. Limitations to usable life of geostationary satellites. When they run out of thruster fuel, the satellites are at the end of their service life as they are no longer able to keep in their allocated orbital position. The transponders and other onboard systems generally outlive the thruster fuel and, by stopping NS station keeping, some satellites can continue to be used in inclined orbits, or else be elevated to a graveyard disposal orbit. Derivation of geostationary altitude. In any circular orbit, the centripetal force required to maintain the orbit is provided by the gravitational force on the satellite. To calculate the geostationary orbit altitude, one begins with this equivalence. By Newton's second law of motion, we can replace the forces F with the mass m of the object multiplied by the acceleration felt by the object due to that force. We note that the mass of the satellite m appears on both sides. A geostationary orbit is independent of the mass of the satellite. So calculating the altitude simplifies into calculating the point where the magnitudes of the centripetal acceleration required for orbital motion and the gravitational acceleration provided by Earth's gravity are equal. The centripetal acceleration's magnitude is where I per mil is the angular speed, and r is the orbital radius as measured from the Earth's center of mass. The magnitude of the gravitational acceleration is where m is the mass of Earth, 5.9736 or 1024 kilograms, and g is the gravitational constant, 6.67428 or plus or minus 0.00067 or 1011 m3 ga 1 za 2. Equating the two accelerations gives the product gm is known with much greater precision than either factor alone. It is known as the geocentric gravitational constant I1/4 equals 398,600.4418 to plus or minus 0.0008 kilometers 3 ZAR 2. The angular speed I per mil is found by dividing the angle traveled in one revolution by the orbital period. In the case of a geostationary orbit, the orbital period is one sidereal day, or 86,164.09054 seconds. This gives. The resulting orbital radius is 42,164 kilometers. Subtracting the Earth's equatorial radius, 6,378 kilometers, gives the altitude of 35,786 kilometers. Orbital speed is calculated by multiplying the angular speed by the orbital radius. By the same formula we can find the geostationary type orbit of an object in relation to Mars. The geocentric gravitational constant Gm for Mars has the value of 42,828 km3 ZAR 2, and the known rotational period of Mars is 88,642.66 seconds. Since I per mil equals 2 I per ton, using the formula above, the value of I per mil is found to be approximately 7.088218 A, 10^5 ZAR 1. Thus, R3 equals 8.5243 A, 1012 km3, whose cube root is 20,427 km. Subtracting the equatorial radius of Mars we have 17,031 km. See also: Geostationary transfer orbit, list of orbits, list of satellites and geosynchronous orbit, orbital station keeping, space elevator, notes. References. This article incorporates a public domain material from the General Services Administration document Federal Standard 1037C. External links: Orbital Mechanics, List of Satellites and Geostationary Orbit, Clarke Belt Snapshot Calculator, 3D Real-Time Satellite Tracking, Geostationary Satellite Orbit Overview, Daily Animation of the Earth, made by Geostationary Satellite Electro-L Photos Satellite shoots 48 images of the planet every day.